All right, recording. Okay, so this is category theory session 13. The reading for this week was chapter 3, sections 1 and 2 on the duality principle and coproducts. So let's just get into that. I will share my notes as usual, and we'll just go over them. Okay, so the first section is about the duality principle. And so the duality principle, Awodey introduces by first reminding us what category theory is. So he tells us, well, category theory has two kinds of things. It talks about objects and arrows. And there are four operations. We can take the domain of any arrow. We can take the codomain of any arrow. We can get the identity on any object, which is an arrow. And we can compose any two arrows, G and F. And this has to satisfy these 7 axioms: that the domain of the identity on A is A, the codomain on identity on A is A, F composed of the identity is F, 1 composed of the identity is F. Sorry, the identity composed of F is F. The domain of F composed G is the domain of G. The codomain of F composed G is the codomain of F, and the composite of so H composed with a composite arrow is, H composed G composed with F. So composition is associative. So given any statement in this elementary language of category theory, we can form a dual statement in category theory by substituting the domain operation for the codomain operation, codomain for domain, and flipping the composition. So F composed with G becomes G composed with F. And then for every statement sigma that we can make in the formal language of category theory, if sigma follows from the above axioms, then so does its dual. That is, if we just take everywhere in sigma where we see domain, we substitute codomain, and vice versa, and we flip all the compositions of the arrows, then we get another statement that is also true in category theory. In fact, category theory is self-dual in the sense that if we apply this substitution to the axioms, we actually get the axioms themselves back. So you can see that the axioms are all mirrored. So if we perform this substitution throughout these axioms, we get the same. That's actually the identity. We get the same axioms back. So then Awodey goes on to say, to state the sort of conceptual version of the duality principle. So he says that for any statement sigma about categories, if sigma holds about all categories, then so does its dual. That is, when we have some statement that holds about all categories, we flip all the arrows, and we still have a true statement about categories. So every statement works in reverse as well. And it's important to note that this doesn't just say that sigma star, the dual of sigma, holds in the opposite category. It holds in the same category as sigma does. So then this has the awesome power of giving us 2 theorems for the price of 1. So every time we come up with something in category theory, then we've actually said 2 different things. And so everywhere where we care to look, we can explore what are the implications if we flip all the arrows. So an example of this kind of thing is coproducts. So we've been talking about products. And so if we take products and we flip all the arrows, then we get a notion of coproducts, which are not the same as products, but a coproduct in C is a product in the opposite category of C. So first, recall the products. So a product is a diagram like this. So it has some product P in the middle. There are arrows going out to the objects A and B, of which P is a product. These projections, P1 and P2. So, for example, if P is the set, A comma B, or is the Cartesian product of the sets A and B, then we can, get an A for every. If we have a pair of A and B, we can get an A, and we can get B with first and second in Haskell. Okay, so that's a product if for every Z, another object in the same category. And we have a diagram that looks exactly the same. So it has Z in the middle with projections into A and B. Then P is a product if for every such Z, there is a unique morphism from U, called U, or that we're going to call U, from Z to P, which makes this diagram commute. That is, P1 composed with U is Z1, and P2 composed with U is Z2. So this diagram here, this familiar product diagram that we've gone over quite a lot so far. So we can form the dual notion, the coproduct, by just reversing all the arrows in this diagram. So we just swap domains and codomains, and we reverse the composition of the arrows. So instead of U compose P2, instead of P2 compose U, we say U compose P2, or Q2 in our case. So then any diagram that looks like this with Q in the middle, and then we have two injections into Q, one from A and one from B. So there are two ways of getting into Q, one from A and one from B. Then Q is a coproduct if for every Z with a diagram that's very much like that, then there's a unique arrow from Q to Z. So we've just flipped this idea. That then makes this diagram commute, okay? So then, great, we have coproducts, sort of totally for free. So then a coproduct of two objects is precisely their product in the opposite category. Then let's take some examples of coproducts. I'm going to keep this diagram on the screen so we can refer to it. So coproduct in Haskell. A coproduct of A and B is just the data type either A, B. So the two injections, are left and right. So we go from A to either AB through left, and we go from B to either AB to either AB through right. This either function here shows that, given Z1 and Z2, we can get U, this unique arrow from Q to Z, where U of left of A is just Z1 of A, and U of right of B is just Z2 of B. Right? So it just defers the application to Z1 and Z2. So it just applies whichever one we actually have. So we either have an A or a B, and we apply Z1 or the Z2, depending on whether we have an A or a B. Great. Awodey notes that every set is a coproduct of one, so the unit set, a number of times equal to the cardinality of the set. So every set is of the form 1 plus 1 plus 1 plus 1 some number of times. And it's number of times equal to the cardinality of whatever set that is. So bool is isomorphic to either unit, or 1 plus 1, or simply 2. And, we can form the 3, whatever.
We're seeing an interesting parallel with that, where I'm trying to remember the article, but it was explaining how to do like church encoding of Booleans to get around deficiencies in some language. And I don't know if that's Sandy's Elm article or something else that I read very recently, but it was interesting to see that in the terms of like church encoding of data as much as it's category theory.
Yeah, Jakob's big on church encodings. So let's, as a reminder, why don't we see what a church encoding of a Boolean looks like. the church encoded Boolean would be like data B, and it would be, B of, for all R, R. I think that isn't that right? It's just that. So I think that's it.
I think so.
So then we can say true is B of, well, it's lambda of R and R1 and R2. This is R1, so it's const. And false is B of, well, flip const, right? And then if, I guess we should say if prime is if prime of B of K, two booleans, B, A and B, is just K of A and B. Oh, actually we can omit this and just say that. Right? So that's great. What does that tell us? Well, yeah, it tells us, so yeah, Boolean is just the set that has two different possibilities. So we need two R's here. If this were a trichotomy rather than a dichotomy, we just need three R's here. And this is true in general for any kind of like church encoding. We will need a function that can take you know, n number of values, for where n is the cardinality of the set that we're trying to church encode.
Yeah, so if you have some arrows U, Z1, and Z2 that are final, then or terminal, then you would get to some terminal, say parentheses right there, some terminal unit, and essentially church encode a coproduct.
Oh yeah, yeah, we could church encode a coproduct where you would have either A, B, which would be for all R, A to R, B to R, to R, right? Which is actually just either. So either of some either is a church encoded either.
Yeah.
Yeah, so it's sort of like a first class fold, right?
Yep.
But yeah, you can see how the cardinality of this set, it's like, it's R to the power of A. Oh, so it's R to the power of B to the power of R to the power of A to the power of R. Right? So it's pretty big, but the size is a function of the sizes of A and B. Anyway, that's a fun detour. Back to coproducts. Coproducts of free monoids. This is a sort of a fun one. So the free monoid of the coproduct of a set is actually the coproduct of the free monoids. So this is not saying that the list of either A, B is the same as either list of A or list of B, which clearly isn't, right? Like these two things are not the same. Like if you have a list where every element is either an A or a B, that's not the same as having either a list full of A's and no B's, or a list full of B's and no A's. This is a coproduct on monoids and not in Hask. So it's not a coproduct on sets, it's a coproduct on monoids. So if what this is actually saying is that the coproduct in the category of monoids of two free monoids, so list of A and list of B. I mean, the free monoid is not exactly a list, but it's close enough So the coproduct of these two monoids is defined as the monoid list of either AB. Right. So it's the free monoid. The coproduct of two free monoids is the free monoid on the coproduct of the underlying sets. Another way of saying that is that the free monoid functor preserves coproducts. So here's some evidence that this actually works. So if we have a monoid N, is sort of our target here. If we can fold our A's into N and we can fold our B's into N, as we have homomorphisms from the free monoid on A and the free monoid on B, both into N. Then we have a homomorphism, a unique homomorphism from the free monoid on either AB into N. And that's just fold map with matching, we pattern match on the either with this either function. And if it's a left, then we apply F on it, and we just put the element in a single element list. And that allows us to make this work. Yeah, so this means that the free monoid functor from sets to monoids preserves coproducts, just like the forgetful functor from monoids to sets preserves products. So if you'll recall that if you have a product of two monoids, you can forget that they're monoids, and then you'll just have the Cartesian products of two sets, right? Because the product of two monoids operates, pairwise or on the elements of the Cartesian product of the sets. But then if we go the other way from sets to monoids, we don't preserve products, but we preserve coproducts. Does everybody follow this reasoning? So like why the coproduct of two free monoids is the monoid of their coproducts? I mean, the coproducts on the underlying sets. Anybody not following this? Okay, cool. Great. So we'll just say that we've bought this. I want to say though that this is not talking about the coproduct of monoids in general. This is only about free monoids, and we'll talk about the coproduct of monoids in general here in a bit. Okay, coproducts of posets. So if we have two posets, P and Q, their coproduct is simply the poset either PQ. So then we have, we have the two posets, and we just have one poset on the left and the other poset on the right. And so it's a partial order. There's no relationship necessarily between the P's and the Q's, but there's some relationship possibly between all the P's and then between all the Q's. But so it remains a partial order. And it works in that it's simply the same as the coproduct on the underlying sets. But Awodey then talks about rooted posets. So a rooted poset has a distinguished initial object 0. So then it has some smallest element. Then a coproduct in the category of rooted posets has to preserve these zeros. So then it's constructed as the coproduct of the posets, and then we quotient by an equivalence relation that then asserts that the zeros are the same. And we'll get to how to formally construct equivalence relation quotients like that using the language of category theory. And that's going to be like 2 sessions from now where we talk about co-equalizers. But yeah, for now, it's just important to note that, we can get these kinds of coproducts, but we might need some extra stuff. We might need to make some additional assertions about the relationships. Okay, so what's a coproduct in a poset? If we view a poset as a category, then the coproduct of two elements, P and Q, is just the least upper bound of P and Q. Just like the product is the greatest lower bound, the coproduct is the least upper bound. So we can see that, we have the coproduct of P and Q has to be greater than both P and Q, or greater than or equal to both P and Q. For any other Z, which is also both greater than or equal to P and Q, the coproduct of P and Q has to be it has to be less than or equal to Z. So then it follows from that the coproduct of P and Q is the least upper bound. So it is definitely an upper bound and is the least such bound. All right. So here we go with coproducts of monoids in general. So this is the really sort of interesting one. And I think that Awodey's explanation of this is really kind of hairy, and I found it sort of difficult to follow. But fortunately, I was able to puzzle through it, and it's something that I'm familiar with I was already familiar with the coproduct of monoids, which helped. So then the coproduct of two monoids, M and N, is the free monoid of the coproduct either Mn on the underlying sets, but we have to quotient it by an equivalence relation. And we have to make it work in such a way that if we have a list of this where empty appears somewhere in the list, then that should be the same as empty not being there. That is, we want to say that these two expressions are equivalent for our purposes, right? So we want to ignore the empties, basically. They disappear. And if we have a situation where we have two M's, so these are both then elements from the underlying set M. If we have two elements in M side by side, remember that M is a monoid. So in the coproduct, which is now the free monoid on M and N, so it's a list of either M's or N's, and if two M's appear side by side, then we add them together using the monoid on M, and that should be the same. And if we have two N's appearing together in the list, then we should smash them together, and that should be the same. Make sense? So we can actually simulate this situation in Haskell. We can make a new type, which is the coproduct of A and B, where A and B should be monoids. I'm actually deferring that constraint until later. But it's important that we don't actually export the data constructor cop or for the coproduct, because we don't want to expose the fact that this is just a sequence. Like, we want to keep it private that this is, that under the hood is a sequence, and we want to sort of just export this as a monoid. Right, so then we can get from A to the coproduct of A and B, and that is just putting it on the left in either, sticking it in a sequence, and then putting the coproduct wrapper around it. Same on the right, we just use right instead of left. And then our monoid has to do this this equivalence relation stuff up here at the top. For the empty, that's pretty easy. That's just the empty sequence. But then there are some special cases. So here I'm using view patterns to look at the first element, to look at the last element of the sequence on the left and the first element of the sequence on the right. So these two sequences are sort of coming together, And I want to look at the elements that are at the intersection. So I'm saying that if on the left, I have a left, and on the right, I also have a left. That is, there are lefts on both sides. So there are A's on both sides of these of this intersection. Then I actually want to add those A's together using the monoid on A, and then prepend that to the second sequence, and then concatenate the two sequences together, right? So I'm making this thing here work. Okay. And then the same thing on the right side. So then if I smash two sequences together, I want to see if both of them are B's, if both of the ends are B's. And if they are, I want to add those B's together and then concatenate the sequences. And that makes this one work. And then I say, otherwise, I just want to concatenate the sequences. And actually, I'm forgetting this one here. That should actually be in inch, I think. Can I actually do that? Or do I need to? Yeah, I actually need to specify that this needs to be an eq, right? And so then I need to say basically like inch left of A, if A equals empty, then cop empty, else, right? And I need to do the same thing for the right-hand side. So basically, I want to ignore menties. I want them to go away if they appear anywhere in my sequence. So anyway, I had this normalization step then that, so given these new injections, that should also work. So the normalization step should say that, well, I can take a sequence of ethers and turn it into another sequence of ethers that sort of preserves that equivalence. That is, it reduces it to a normal form where there are no adjacent m's, no adjacent n's, and there are no empties. And once I get there, I can now write this sort of fold cop, which allows me to fold this coproduct and pretend that it really is a coproduct. So then this thing here sort of proves that this really is a coproduct. So if I have a monoid A and a monoid B, then for any monoid Z, if I have the coproduct of A and B, I can fold that into a Z given arrows from A to Z and B to Z. So this is the coproduct diagram, right? So given F and G and my coproduct, I can simply pattern match on every element in my sequence, do the F on the left, do the G on the right, after I normalize the sequence. And forget what I was going with this thing here, but yeah, you can see that you can take this coproduct and you can get out of it the product of A and B. So you can fold the sequence and get all the A's and all the B's and sum them up, right? And that's going to be important when we talk about abelian groups. But yeah, so in a monoid, so we can sort of get a product out of our coproduct. And that is just like we fold our coproduct with these two injections where we start with the empty B if we have A's, and we start with the empty A if we have B's. Right? And I just made this show instance so that I could actually try this out in the REPL. So yeah, any questions about this or concerns or any skepticism about whether this is actually a coproduct?
Seems good. It's pretty interesting.
Yeah, I have actually a blog post, which I will go to. About mono coproducts. Might be helpful. I'll put that on the screen now. So yeah, it's called Monoid Morphisms, Products, and Coproducts, where I talk about products and coproducts of monoids. And it has all these cool diagrams, but the coproduct thing, I actually gave a proof that this really is a coproduct. Like I asked the question, is the fold of the coproduct really a homomorphism? Like, does the monoid homomorphism law really hold? And like, I make an attempt at the beginning where it doesn't hold, and so it was sort of an eye-opening experience to just like try to puzzle out what would be the coproduct of two monoids, like before I knew what it was. So this is my sort of struggle through that. So that's fun. So that's at blog.higherorder.com. Okay, so back to coproducts. Okay, so coproducts of groups, very similar to coproducts of monoids. A reminder of what a group is. Well, a group is a monoid that has an inverse. So for every element A of the monoid, we can get the inverse of A, or the negative A. So we can get a free group for any set A. And so that's very similar to a list, except it has negative lists as well as positive ones. So, you can think about how you would implement that. But the coproduct of two groups is very similar to the coproduct of two monoids. And the coproduct of two groups is called their free product for historical reasons. The free product, the free product is like the free group of a given set is like a list, but it has inverse lists. So yeah, the coproduct of two abelian groups is now a little more interesting, and Awodey says is more important. A reminder of what abelian groups are. Well, they are groups that are commutative. So then the addition or the multiplication operation in the mapend, as it were, is commutative. So since the group is commutative, then we have this list, but the order of the elements in the list now doesn't matter. Like, we can commute the elements past each other, and that should be equivalent, right? So really what we can do is shuffle all the A's to the front and all the B's to the end. But then once we have all the A's on the front, we can just sum them all together. And if we have all the B's on the end, we can sum them all together as well. And now we just have a pair, an A and a B. So the coproduct of a commutative group is isomorphic to the product. So that's kind of cool.
What's this inverse list thing?
Oh, what's an inverse list?
Yeah.
Well, it's totally free, right? So it's basically like completely vacuous.
Right.
Do you follow that reasoning?
No.
Okay. Well, let's pretend that the free monoid is a list, right?
Right.
So then the free group let's say data 3G. Well, so it's not just the list of A, right? Because that would just be the free monoid. We need that for any A. We also have an inverse, right? So actually,
Yep.
I mean, for any element in our free group, we have an inverse. So actually, it's something more like, let's just say inj of A and inv of A, right? So that's something more like that. Make sense?
But there's some laws that have to hold between these two lists, right? Like the A's in this list somehow annihilate each other.
So that's the meaning of inf is unspecified. It's free.
I'm so confused. I guess sure.
So we can do this like a list where like, oh, it's either the empty, so the menti of the group of our free group, or it's an A. It's called cons. It's an A together with another free G of A, right?
Right.
Or it's an inv of a free G of A.
Okay.
Right, and what this means is not specified here.
Right, because it's free.
Right, it's for all group G, actually for all G, given that G is a group, we can go from free G of G to G.
Right.
Actually, we can go from free G of A to G, given a map from A to G. Right.
Yeah. Okay.
So that's the free group. And then the free abelian group, it would be, I don't know. You would have to have so this is an associative operation here because everything associates to one side. I guess you'd have to have a set then for a free abelian group, right?
Would be a yeah, I guess it would have to be a set.
Yeah. Because like then the order has to not matter. But yeah, then the cool thing about coproducts on commutative groups is that since you can commute all the elements past each other, then you can just like, oh, hey, I could just have a product. I can just have two elements and I'll keep all my A's over here. I'll keep all my B's over here. And so what you actually end up with is isomorphic to the product. Wanted to give a couple of other examples. So the coproducts of relations is the same as their product, because if you'll recall that the coproduct, the product of two relations is the disjoint union of the two relations. We went over that when we were talking about products, but that actually happens to be the same thing as their coproduct. And the reason is that if we flip the arrows, and you'll recall that the arrows are Cartesian products, so the relations or the elements in the relations are pairs. And so if you just flip the pairs, you still have a pair, right? And so the product of these things are going to be the same. Empty coproduct, right? So just like we have an empty product where empty product was the unit, right? So it's a product of no objects. We can have an empty coproduct in a category C, which is just the initial object or its initial object in C. So given no object and no arrows, we have our coproduct diagram, this triangle thing. If we cut off the two ends of the triangle, we just have that central arrow going from the coproduct Q to every object Z, no matter relations to anything else. And that's the same as an initial object. So it has a unique homomorphism into every other object Z, no matter what. So we can picture the coproduct diagram and just cut off the A and B. For example, in Haskell, the empty coproduct is the empty set. We call that void. And there's a unique homomorphism, which is the empty function void to Z, which has no implementation at all. I'm not actually sure that you can express that in Haskell, but I mean, you can sort of simulate it by giving this type signature and just like saying undefined. Because there's no way anyone could actually call that function anyway. I mean, what are they going to pass? I guess you could pass undefined. Okay. Then coproducts of categories. We can get the coproduct of two arrows in any category. And that just works as follows. If we have one arrow from A prime to B prime, another arrow from A to B, we can get an arrow from either A prime or A to either B prime or B. So basically, it's just this construction where we have a pair of arrows, and if we happen to have an object on the left, then we apply the left arrow. If we happen to have an object on the right, then we apply the right arrow. And so this gives rise to a coproduct functor from the product category of C to C. So given an element, given an object in this category, which is, given an arrow in this category, which is a pair of arrows in C, we can get an arrow in C, which is an arrow like this. So it takes pairs of arrows in C cross C to their coproduct as above in the category C. Great. So here comes the awesome thing. So let's prove that coproducts are unique, all right? So we have previously proved that products are unique. So we just say dually for coproducts, and we're done.
Damn it.
Thus, it is demonstrated, right? So it's, we can go to our definition of, so I might have somewhere. Come on. Oh, I have inverses are unique. Oh well. No matter. It's somewhere. We have the proof that products are unique. And well, by duality, we also have the proof that coproducts are unique, which is pretty great. So that's all I have. And that concludes section 3.2. Anybody else have anything? Questions or concerns? All right. Is this useful?
Yeah, thanks, Renard.
Awesome. Well, I'll see you guys next time. Next time, I'll see you guys in person.
Oh, yeah.
Yeah.
All right.
See you at the audience.
Later.